Good afternoon everyone. Sorry for the great amount of delay. Today we are starting a new seminar series on the Math Club titled What Is. So What Is has been inspired from the AMS notices column which is titled the What Is, and there is also a talk series in Berlin Mathematical School titled What Is. So Aaratrick here, he came up with this idea that we should also organize something like that, and that's why we are having this What Is now. The What Is will go on for the entirety of March. We will be having talks thrice a week, on Friday from 9 pm to 10 pm, on Saturdays from 3 pm to 4 pm, which unfortunately today got delayed a bit, and on Sundays it will be from 11:30 am to 12:30 pm. So today's speaker is Aaratrick Basu. He will be speaking on what is question mark function. Aaratrick is interested in geometry and topology from a group theoretic aspect. The idea for this question mark function was given to us by Professor Suri back in January, when we first mailed about this What Is series, and he thought that this will be very interesting to see on the projector what is question mark. So up to you, Aaratrick.
Thank you. So sorry for the delay again, and let's begin. So this talk is going to be about this function which Minkowski introduced back in the early 1900s, called the Minkowski question mark function, and written with this, awkward but at this point standard notation of question mark of x. So let us begin with this very basic question of counting the rationals. So I think everybody here is familiar with this standard proof, which is sometimes miscommunicated as Cantor's diagonal argument, but this is not really that. So this is done by arranging the natural numbers in this sort of rectangular grid and counting the rationals along the diagonals, like this, so here, and so on, right? But if you notice something, this is not really a bijection but a surjection, because for example in this principal diagonal the number 1 occurs infinitely many times, right? So it's of at least recreational interest to ask the question of whether we can get an explicit bijection from the naturals to the rationals and vice versa. So before that these are two other explicit bijections from n cross n to n, defined as follows. You can take it as an exercise to show that indeed these are bijections. But again, the problem is that when we replace, when we try to identify m comma n with the rational number m by n, one will occur, for example, infinitely many times, and so this won't remain a bijection from the rationals. So to address the question of the explicit bijection, we need to define this operation called the Faraday sum or the median. So this is basically what a school child would make a mistake of while adding fractions. So we'll define p by q median r by s as p plus r by q plus s. Okay. And so then we construct this tree called the Stern-Brocard tree. So after the mathematician Stern and clockmaker Brocard. And so it's constructed in this fashion. So you start with these two numbers, 0 by 1 and 1 by 0. So of course 1 by 0 is not really a real number, but we just put it here for the sake of construction of this tree. And you take successive medians. Okay. So when you take the median of these two, you get 1 by 1 of course. And then when you take the median of 0 by 1 and 1 by 1, you get 1 by 2. And here you get 1 plus 1 by 1 plus 0, which is 2 by 1. So if I go one generation further, you get 1 by 3, 2 by 3, 3 by 2, and 3 by 1. And finally, one more generation gives you 1 by 4, 2 by 5, and so on. So as is pretty obvious, intuitively at least, is that all rationals will occur, and in fact will occur exactly once. And formal proof can be given by deriving can be derived by giving a formal recurrence for the terms appearing on the nodes. And the point of this tree is that if you look at the left half of this tree, the rational numbers that occur will be strictly in 0, 0, 1, and the ones on the right will be between 1 and infinity. So we now focus on this left half, and that gives us this tree which is called the Faraday tree. So this is just the left half of the Brocard tree focused on. So you start with 0, 1, 1, 1, and go to 1 by 2, 1 by 3, 2 by 3, and keep repeating using the same construction. So another perhaps more familiar tree is called the dyadic tree, and here what you do is you just take, instead of the medians, you take successive averages. So you start with 0 by 1 and 1 by 1. Take the average, get 1 by 2, take the average between these two, get 1 by 4, between these two, get 3 by 4, and so on. So if you notice something, so as I all rationals in 0, 1 will appear exactly once here. But as we all know, the rationals that appear here are only the dyadic ones, in the sense that they are the numbers with denominators powers of 2, right? So, but again, we can, because of the dyadic expansion, we can consider any rational number occurring as a limit of this tree, in the sense that we can try and go down infinitely many steps along this tree and approximate any rational or even irrational for that matter. And we can do the same over here and approximate irrationals in 0. So in some sense, the limiting version of this tree with paths going off to infinity gives you in some sense an enumeration of 0, 1, which is not really an enumeration, of course, because that is uncountable. But yeah, so we'll come to that shortly. So now we come to the actual definition of the question mark function. So it is defined as the basically taking the Faraday tree and mapping the nodes of this tree to the corresponding nodes of the dyadic tree. So for example, it will map 0 by 1 to 0 by 1, 1 by 2 to 1 by 2, 1 by 3 to 1 by 4, and so on. So it's pretty clear. You just take the some node here, note down the number, and you define question mark of that number to be the value which appears in the corresponding node in the dyadic tree. And again, so at this point the question mark function is defined only on the rationals in 0, but as I remarked, we can consider the irrationals as limits of the Faraday tree, and so we'll come to a formal definition shortly, but we can extend the definition of question mark by continuity to all reals in 0, 1, right? Okay, so just to summarize the properties, we have question mark of 0 is 0, 1 is 1, half is half. As an example, we have 1 by 3 is 1 by 4, and the most important property is that the question mark function maps the median to the average. P by Q, Faraday sum R by S maps to this thing. And the last property that I want to focus on is on the monotonicity. Question mark turns out to be a strictly increasing function. So to view this, let's go back here and look at the Faraday tree more closely. So if you look at this tree, you can sort of see it here that the tree is like monotonically increasing, in the sense that the numbers on one level are always greater than the numbers on the next level, and a similar relation holds in between the numbers that appear at any particular given level. So basically, if you have two trees, 2 points x and y in 0, 1, maybe irrational considered again as limits, what you can do is you can locate the corresponding limiting paths here from half, for example, and if you go back to the if you take the question mark map to the dyadic tree, the corresponding images will satisfy the same relation, in the sense that if x is less than y, then question mark of x will be less than question mark of y. So to make this more formal, what you do is you define a lexicographic order in the left and right steps along this tree, because all of these trees are binary branching, so you can do that and just write out the thing and you'll get a formal essentially. So that sort of gives a visual proof of the monotonicity of question mark. And so we now proceed towards the analytic definition. So for this we need to recall what are continued fractions. So this notation means that x is the continued fraction 1 by a1 plus 1 by a2 plus dot. So note that we are using the notation where, because all our numbers throughout this talk will be in 0, 1, we are omitting the integer part, in the sense that there is a 0 in front of this, right? So the convergents here are pj by qj, which is just up to a, if you truncate this expression up to aj, and pn by qn is exactly x. So let yj be the image of the jth convergent, and note that this is the median property that I mentioned earlier. You get that question mark of this thing is this thing, because by definition yk is the image of this and yk minus 1 is the image of this, right? And then by induction what you do is, this is actually a property of continued fractions, that these two things are always irreducible, in the sense that this fraction ak plus 1 pk plus pk minus 1 by ak plus 1 pk plus pk minus 1 is in lowest terms. And if you note that this, if you go back to the definition, you will find that this is exactly pk plus 1 by qk plus 1, the k plus 1th convergent. So that's why I've written yk plus 1, which is the image of this thing, is yk by 2, so on up to yk by 2 to the power ak plus 1 plus yk minus 1 by this. And so just take noting question x is yn, we get this expression for the for any rational number in 0, 1. That question mark of x is 2 times summation minus 1 to the k minus 1 by 2 to the power a1 plus dot ak, and we simply extend this definition by continuity for the irrationals and get that if you have an irrational with a limiting continued fraction expansion of this form, you define your question mark of x to be this thing. Note that this definition is not an independent definition. This is exactly doing what we did with the Faraday tree and the dyadic tree and rewriting it in terms of the continued fraction expansions. And you can actually sort of understand why this is happening if you try to understand how the continued fractions and the convergence of any given rational or even irrational will occur on the nodes of the Faraday tree and look at the corresponding nodes of the dyadic tree. So another interesting thing to note here is that we are actually not using the usual dyadic system where the allowed coefficients are 0 and 1. We are using what is known as the alternating dyadic system, where we allow both -1, all three of -1, 0 and 1. But again, it's easy to prove by induction or otherwise that every real number, for example in 0, 1 will have a unique alternating dyadic expansion up to the fact that terminating expressions will have 2, but they will end. Right? So that's that. And so we summarize the properties that are now evident from this analytic definition. So we had this property since before the monotonicity, but now we have continuity as well formally. We have the fact that question mark will map rationals in 0, 1 to dyadic rationals. So to see this, just look at this. So if you have a rational, it will have a finite continuous fraction expansion of this form, and so question mark will be something of this form, which quite obviously is a dyadic rational. If you given an irrational input, question mark of x will have infinite dyadic expansion. Again, simply because the continued fraction expansion is infinite. But more interestingly, and this was the original motivation of Minkowski for defining this function, he was trying to understand how quadratic irrationals can be related to dyadic expansions. The property of question mark, which is most probably the most important property of this thing, is that it will map quadratic irrationals to rationals with infinite dyadic expansion. So these are because of the fact that a number is a quadratic irrational if and only if its continued fraction expansion is infinite yet periodic. And so when you go back to this expression, you will basically get repeating blocks of finite dyadic rationals. Sorry, not that one, this one. And so it will end up being a rational, but it will have infinite dyadic expansion. Right. So these are the main properties that we have so far. And so now we come to some more, say, graphical properties. We'll talk about what is called the fractal nature of the graph of question mark of x. So the graph is exactly this set x comma question x. X in 0, 1, this is treated as a subset of the unit square, and this is an image that's available on the Wikipedia page. And I mean, so the important thing right now is I would like you to focus on the self-symmetry of this thing. So one property which is sort of obvious from this figure is that question mark of x plus question mark of 1 minus x will always add up to 1, and that is obvious even earlier. So if I go back to the Faraday tree again, if you notice that, say for example 1 by 4 and 3 by 4 add up to 1, 2 by 5 and 3 by 5 add up to 1, and sort of a similar thing holds at each level, and the same relation holds even on the dyadic. So that gives you that symmetry. And the other symmetry will come from the analytic expression. So the obvious symmetry, as I mentioned, is question mark of 1 minus x is 1 minus question mark of x. And the definition, the analytic definition of question mark gives us the symmetry x by x plus 1 maps to question mark of x by 2. Because of the fact that the operation x going to x by x plus 1 is the same as this operation on the continued fraction, you basically just increment the first integer appearing by 1. And you can just verify that this holds from the analytic definition. Easy. Right. So we abstract this out and define these symmetry operators Sxy and Rxy. So these are symmetry operators on the unit square, and they describe the self-similarity symmetries of gamma. So Sxy is just 1 minus x, 1 minus y, Rxy is x by x plus 1, y by 2. And what can be in fact shown is that all the self-similarity symmetries of the graph gamma are of the form r to the a1, s, r to the a2, so on up to s, r to the an, where I've used the fact that s is an involution, s square will give you the identity, right? And note that this, you cannot plug in r to the power minus 1, for example, because this is not a bijection from the unit square to itself, whereas this is, right? So what this does is it basically shrinks the unit square. If I go back to the figure, it shrinks the unit square to its bottom left half square. So yeah, it's pretty clear. And so we can represent SNR as Mobius transformations by defining f of x to be 1 minus x treated as the matrix minus 1, 1, 0, 1 acting on x. So here we are using the usual convention that the integer matrix or even real matrix ABCD acts on a number x by the modulus transformation ax plus b by cx plus d, and so it's basically just minus x plus 1 by 1, and similarly r of x equals x by x plus 1 gives you this thing. So note that this matrix has determinant -1 and this matrix has determinant 1. So as I said, you cannot plug in r to the -1. So what you get is not a subgroup but a submonoid generated by R and S. So a monoid is basically just a group, but certain elements don't have inverses. So that's what you have here. And so this is a subset of PGL2Z, where PGL2Z, if you recall, is the projective general linear group. So the general linear group over the Z over Z consists of all matrices having determinant either 1 and -1, because these are the only units in this ring. And so by P, I just mean that we identify any matrix with its negative, because that doesn't change the fractal linear transformation that you apply. Right. So this monoid has a name. It's called the dyadic monoid or the period doubling monoid. So the reason for that is there's a wide class of fractal curves that whose self-similarity symmetries are described by this monoid, and so we briefly talk about those. So very interestingly, these curves were actually completely described by Georges Dirac, the same guy after whom Dirac cohomology is named, and we'll have more to say about cohomology next. But for now, we focus on metric spaces. So suppose M and D is n comma D is a complete metric space, and F0 and F1 are two contracting maps. So contracting here just means contracting in the sense of a metric. So D of F0 x, F0 y will be less than D of x for any x. That's what I mean. Right? So now the standard theorem from metric space theory, the Banach fixed point theorem, guarantees that there will exist two fixed points P0 and P1 of F0 and F1 respectively. And so now we will consider a different kind of map. So fix some number x in 0, 1. Expand it in the usual direct system. So here bk's are just 0s and 1s. And consider this map Cx, which is defined on M to be this thing. Fb0 compose Fb1, so on up to Fbk compose and so on. Right. So if you have a finite expansion, this will be a finite composition, and otherwise it will be an infinite composition. So we need to address why this thing makes sense in the first place. So the point is that F0 and F1 are contracting maps. So to visualize it in some sense, you have your big space M, and each iteration of either F0 or F1 maps it onto a smaller set. It maps it in the proper subset of it, right? So if you keep on repeatedly applying, because the sum in fact converges to a given real number, this composition will make sense with one other condition. This condition that we demand that F0 P1 is F1 of P0. So what is this condition saying? So this is saying essentially that recall that P1 is fixed by F1 and P0 is fixed by F0, right? So what this is saying is that your basin of attraction of F0 and the basin of attraction of F1 are intersect, they are not disjoint. So what this condition imposes is that this at each iteration you get a proper subset of this intersection, and so repeatedly applying either F0 or F1 cannot increase it or cannot even shift it, rather it will keep on making it smaller and smaller inside that common basin of attraction, and so this infinite composition makes sense. Right. A more formal proof can of course be given, but this is the essential idea here. Right. So actually what can even be shown is that if you assume this, then Cx will be a continuous curve under the given metric, and what can be shown is that Cx will map the common basin of attraction of F0 and F1 to a single point Px. So now finally this curve x going to Px, which is a basically a curve in 0, 1 cross m, right? Px is a point in M. So this curve is the image of this curve is in 0, 1 cross M. This is the Dirac curve associated to F0 and F1, right? And actually even the points P1 and P0 in case the Fi's have multiple fixed points, right? So what is true is that the Minkowski quotient functions graph is a Dirac curve. We haven't shown it as a Dirac curve here. This is just the usual curve, and so this is just in this can be shown that it turns out to be generated by these two maps. F0 of z is z by z plus 1, and F1 of z is 1 by 2 minus z, where we are identifying C with R2 in the usual sense, right? So some more pictures. So here, first of all, I'd like to clarify that this picture is, so the metric space in picture is R2. So this figure should really be in R3, but for the sake of clarity, this is just the image of the curve in R2. So basically the parameter x, which is varying in 0, 1 is not shown. This is just the image of the curve. So this is a class of curves called the Cesarov-Favor curves. These are generated by these linear maps f0z az equals az and f1z equals a plus 1 minus az. And so, of course, we need to assume that mod a is less than 1 to get these are contracting maps in the first place. So the fixed points here are of course 0 here and 1 here. So next, there's another famous curve in fractal curve theory called the Levi-C curve, and we can actually identify this as a Cesarov curve with this particular parameter a equals 0.5 plus I 0.5. And so here first, I didn't mention this is the curve with parameter 0.3 plus I 0.3. Right. So some more examples. So apparently this is not clear why this should be a Dirac curve for anything, what this has to do with anything that I spoke about. So this is the very famous Pope snowflake. So how you build it up is you start with an equilateral triangle, trisect each side and put up smaller triangles and keep on doing this. And so what you end up as the limit is a figure with infinite parameter but finite area. Another of the same flavor is the piano curve. So here the construction is a little bit more complicated, but you start with something on the figure that I show on the leftmost, and basically you consider the grid here and you subdivide it into several smaller squares, put in some and remove some and get this figure. But if you notice that this is sort of similar, right? Here there's three things. I mean, you can sort of see that it's similar, and the limit it will actually be like if you zoom in at any point, you get the same figure, right? So what you can do is actually identify both of these factors with a wider class called the Pope piano curves. So these are the Dirac curves generated by f0z equals az bar and f1z equals a plus 1 minus az bar. And so this is the curve for parameter 0.6 plus I 0.37. And you can actually get the Pope snowflake and piano curve as figures here using certain specific values of the parameter a. So another interesting curve which sort of illustrates both of the previous ones in some sense is the Takagi-Landsberg or Blankmann's curve. So this was described first by Takagi, and later Landsberg also worked on it and gave it the name Blankmann's because it somehow, for certain values of the parameter w, it resembles what is called the Blankmann's pudding. So this is sort of the most general case of a fine Dirac curve. So these are the Dirac curves which are generated when you take f0 and f1 to be oh, I have typed it. This should be f0, this should be f1, but yeah, doesn't matter. So what you do is you take f0 and f1 to be affine maps on the complex line with the identification that 1xy is the complex number x plus I. Right. So with these particular affine maps, you get this curve for the specific value w equals 2 by 3. So what Dirac showed that in his paper on Dirac curves is that in general Dirac curves are just continuous once you impose that condition of there existing a common basis of attraction. But in general, if you start with an arbitrary metric space and contracting maps, it will not be differentiable. But that is not true. It is not true that all Dirac curves are non-differentiable precisely because of this example, where it is known that for the value w equals 1 by 4, this is an exact parabola and so smooth. Right. So that's all about the self-similarity, and now we move more towards some analytic properties of the question mark function. So we address the question of Lipschitz continuity. So Salem in his 1943 paper, so by the way this is the same Salem after whom the Salem Prize is named, and I mean he has done a lot of work in the analysis of real functions and so on. But well, so he proved this theorem that the question mark function is actually a Lipschitz function of this order, half log 2 by log 5, where phi equals 1 plus square root 5 by 2 is the Fibonacci, is the golden ratio. And in fact, this number, this thing is the Holder exponent in the sense that you cannot do better than this. This is the best possible order for your Lipschitz continuity that you have here. So the proof actually follows from this sort of number theoretic and analytic fact that if you have a rational number, p by q is the finite continuous fraction expansion a1 an, then this inequality holds. Q is less than 5 to the power a1 plus order an. And so basically what you do is you use your analytic definition for the question mark function. Recall that it has those it has an alternating diagonal expansion with the digits exactly being placed in the places a1 plus dot dot an, right? So and after that it's basically just a simple computation which anybody after first analysis can do actually, and show that this holds, and to show that it is in fact a Holder exponent, you actually put in the irrational number 1 by 5. 1 by 5 will belong is an irrational in 0 1, and you show that for that particular number you cannot do better than this order. So next we address the question of the derivative. So the first thing is that the question mark function is a strictly increasing continuous function. So we know from standard real analysis that it's a function of bounded variation and hence has derivative almost everywhere, right? So what Fallon actually showed is that it is what is called a singular function, in the sense that the derivative wherever it exists is actually 0 for almost all x. So just a remark, slowly after this slide we'll use some rudiments of measure theory, but all you need to know for this talk is measure 0 and measure 1. So measure 0 just means a very small set, and the complement of a measure 0 set is a measure 1 set, and that's just for our purposes because all our numbers are in 0 1, it means that for almost all numbers in 0 1 that property will go, right? So let's come back to this proof. So the idea is that you give an explicit set where the question mark, the derivative question prime exists and is finite, and certain other properties will hold, which will force your derivative to be 0 necessarily. So what you do is you intersect these two sets. So it is known that x equals a1 dot an, infinitely many, the set of such irrationals in 0 1 such that lim sup of an is infinity is actually a measure 1 set. So almost all x in 0 1 satisfies this, and like I mentioned, it's a question mark is a bounded variation function, and so this set, the derivative exists almost everywhere. So now another fact that you need to know is that if you intersect two measure 1 sets, you end up with another measure 1 set, which is sort of intuitively clear. So you basically should get that this set is of measure 1, and what you do after that is show that because of this property, the lim sup being infinity, if your derivative is finite, it must be 0, as otherwise what will be violated is essentially the an going to infinity in some sense. But well, the proof is a little bit technical, so I've omitted it, but it's nothing too hard, and you can follow the proof in Fallon's original paper, right? So we will demonstrate another singular set of question marks. So singular set is just a set of measure 1 where derivative will exist and will vanish. So for that we need this definition of an asymptotic distribution function. So suppose you start with a sequence an where each an belongs to 0 1, and you define its asymptotic distribution function to be this real valued function on 0 1 as well. So it's essentially the proportion of ai's in average that are less than equals to x. So for each n from 1 to infinity, you restrict to a1, a2, an, count the number of ai's that are less than x, and take the average and basically take the limit. So it can be shown that the asymptotic distribution exists for most well-behaved sequences, and so it will exist for the sequences that we care. So what are the sequences that we care? So it's this goes back to Gauss. He defined this map, which is now called the Gauss map, from open 0 1 to close 0 1, which is essentially hx equals 1 by x mod 1, which is nothing but the fractional part of 1 by x. So what he conjectured and Kuzbin later proved in the 1900s is that this set G of the values x in 0 1 such that the orbit h and x, so this orbit is essentially just x, comma x, hx, h square x, and so on. This sequence will have the function log base 2 of 1 plus t as its asymptotic distribution almost everywhere. So the set of x for which this property holds is of measure 1, right? And so we call the set of this set G to be the set of Gauss-Kuzbin numbers. So essentially it's a set of numbers for which exactly log base 2 of 1 plus t is the asymptotic distribution, right? Now, to relate this to the question mark, we go back to this definition. So as I mentioned, this is expanding irrationals in or any reals in 0 1 in this alternating dyadic expansion. So if you try to compute for an arbitrary x and you didn't know what question of x is, if you wanted to compute the digits, so basically by digits I mean the indices for which where these coefficients are non-zero, these a1 plus dot ak, for example, here. If you wanted to compute for an arbitrary x in 0, 1 where these things are non-zero and explicitly what the coefficients are, this particular function turns up. This is called the residue function of the alternating dyadic base, and it's defined in this way: 2 into 1 minus 2 to the power nxx, where nx is this thing, log base 2 of 1 the integer part. Right. So now a definition is, we call a number in 0, 1 to be normal in this base alternating dyadic base if the orbic of x under this residue function f is uniformly distributed in 0, 1. So this exactly resembles the usual definition of normal numbers in the decimal system. In some sense, you want to know what are the numbers whose digits are uniformly distributed in your base. So for decimal, for example, you want the numbers whose basically any digit in 0 to 9 is equally likely to occur in the expansion at any given place, right? So that's the definition here, just for the base alternating dyadic system. And so what can be shown is that this function f preserves the Lebesgue measure and is in fact what is called an ergodic map, but we don't need that right now. So what a consequence of just the fact that f preserves the Lebesgue measure is that for almost all x in 0, 1, the orbit under f is indeed uniformly distributed, and hence the set n of normal numbers is of measure 1. So contrast this with the usual proof. The usual proof is purely existential, and just like here, you just have the fact that any number is almost surely normal in base 10, but you actually don't know for any given number whether it's normal, except for some very, very specific cases. So, but all we care about right now is that indeed this holds for almost all x. Right. So what is the theorem here? So the theorem here is that the Minkowski question mark function maps this set G intersection n and the inverse image of this set G intersection n into so the measure of these two sets is 0 in both cases. So what is this saying? So recall that G is measure 1 being the set of Gauss-Kuzmin numbers, n is the set of normal numbers in the alternating dyadic base, and hence again of measure 1. So this set G intersection n is also of measure 1. So what we have gotten is a set of measure 1, both of whose image and pre-image are of measure 0. And so if you intersect this further with the set where the derivative of question mark exists as a number, we get another set of measure 1. And what is an easy exercise once you know some measure theory is that any strictly increasing continuous function, I think you don't even need continuity, but maybe here we have that. So if you have a strictly increasing continuous function and you have a set S where its derivative exists and is finite, and that set is of measure 1, and the function maps it to a set of measure 0, then in fact the derivative must be 0 everywhere on that set. So this gives us another singular set. So why did I bring this up? So we won't discuss this any further today, but this has deep connections with dynamical systems and what is called the Gauss-Kuzmin-Welsing operator in ergodic theory. And there's a lot of number theory, measure theory, and dynamical systems and fractals involved here. And I hope people will take it on themselves and explore it a little further later. But yeah, so what next? So Fourier series. So this is perhaps the most technical part of this talk. And so the question mark function, as I've shown, is a strictly increasing continuous function, and restricted to 0, 1, we can think of it as a periodic function on R or on the circle, for example. And so it has a Fourier series, not a Fourier expansion, Fourier transform, but a Fourier series. And you can ask the question of how does the coefficients decay in the long term. So actually Salem in the same 1943 paper raised the question of is it even true that Cn, where Cn is the nth coefficient of the Fourier expansion of question mark, goes to 0 as n goes to infinity. What is showed using some standard theory of Fourier series available at the time is that if you restrict yourself to the behavior in the average, so C1 plus C2 plus or Cn by n, if you consider sums of this form, he showed that in fact this is decaying to 0 and infinity. Not only that, but in fact decaying polynomially. So in the sense that this sum is O of n to the power minus eta for some suitable eta greater than 0. So this is very recent work from 2015, which has actually related the Minkowski measure question mark prime with what are called Gibbs measures, and from some general theory of that, you conclude that actually the Fourier transform, even the Fourier coefficients decay polynomially as n goes to infinity. So basically, Salem showed that on average you have O n to the power minus eta. Now we actually know that even Cn is O n to the power minus some xi for suitable xi greater than 0. And it's much more involved, because what you actually need is certain properties of the measure mu hat, in the sense where you need certain properties of the measure defined by the Fourier transform, and you need to know what the Hausdorff dimension of that is, and certain technical conditions then give you this theorem. But okay, and what about other Fourier integral transforms? So there's been a lot of work since 2000 in the 21st century on other integral transforms of the question mark function, and relating this to other number theoretic as well as analytic aspects of fractals and other dynamical systems. And so we won't have time to mention that here. Finally, the most interesting aspect is probably it's the connection of question mark with modular forms. Actually not modular forms, but what are known as certain generalizations of the modular forms, known as quasi-modular and mean modular forms. So what is shown is that a certain generalization of the question mark function to the real line, which restricts to the usual question mark on 0, 1. If you consider its derivative and consider certain integral transforms, the algebra generated by that, in some sense, the algebra generated in some sense is actually isomorphic to the algebra generated by the Eisenstein series E2, E4 and E6, which is exactly the algebra of quasi-modular forms. And so that brings up this whole question of how exactly are we relating this question mark function with modular forms, which somehow should not turn up at all, right? But well, it all goes back to the fact that question mark essentially converts number theoretic properties of irrationals in 0, 1 to analytic properties exhibited by the function. And so somehow, if we go back to the very beginning, maybe some of you have already noticed if you've seen these trees before, what is true here is that the children here, say for example 1 by 3 and 2 by 5, they exhibit what is called unimodularity. So in the sense, if you multiply 5 into 1 and 3 into 2, the difference has absolute value 1. And a similar relation holds between these neighbors as well. Not these neighbors, but certain neighbors here as well, right? Yeah, so actually, yeah, I think that it's true here. Yeah, these two, right? So that already brings up the question of relating this with the modular group, and so there are a lot of arguments, of course, and you can actually relate with the Faraday tree with the modular group PSL to Z, and hence you finally get how question mark is converting certain properties of the modular group into certain analytic properties of this function, and that is how you get the connection. And so I'd like to end with that. So thank you. So any questions?
Are there any practical which is not being answered?
Yes, so very interesting question. So yes, there are such fractal curves, but the ones that you construct in a similar fashion as this. So for example, if you consider the Cantor function, so essentially what is true is if you want to get your fractal curve from a singular function defined as here, you end up with a Dirac curve in most cases. But if you start with something like the Mandelbrot set or the Julia set, those are not Dirac curves. So there are fractal curves which are not Dirac curves. Yeah.
Can you once go back to the asymptotic distribution?
Yeah.
Yeah. Maybe I didn't hear that. What is the use of this?
So this is essentially measuring the distribution of the sequence an instead. So usually in statistics or probability we have a sequence of random variables and we speak of its asymptotic distribution. But here we have a definite sequence, and we want to ask the question of how this sequence is distributed in a given set. So here, for example, we are working in 0, 1, but we can work in an arbitrary bounded interval or even in a compact metric space, and consider maybe not metric space, but here. So consider this kind of distribution, and this is basically sort of the beginning of the theory of equidistributed sequences and asking how a given number theoretic sequence or any other sequence for that matter is distributed in your image set. So this is one particular measure of that. So this is one example of a theorem, and many more such theorems actually hold. So the theory of normal numbers, for example, has a lot of such things. So yeah.
Are there any more questions?
And you mentioned that the Fourier coefficients they are picking what is that psi?
So the xi is a very technical number. It comes out of the Hausdorff dimension and stuff like that. It's some positive number. But what is interesting is that we do in fact have polynomial decay even here, and this is actually so I didn't mention it here, but this is actually a widely studied problem of whether a given function is a Rachman measure. So a Rachman measure is exactly one which arises as a Fourier transform and decays polynomially at infinity. So basically the theorem that it was proved in 2015 is saying that the Minkowski function is gives rise to a Rachman measure. So yeah.
Are there any more questions?
Sorry for the delay again, and hope you enjoyed this talk. And I hope the audience will take it on themselves to explore some of these topics, because it really is not possible to do justice to all the various aspects here, because even the Faraday tree itself has a very beautiful theory on it in and of itself. So yeah.
So, if there are no more questions, let us thank Aaratrick again for his wonderful talk. Oh, right. Okay, so continuing this series of talks, and tomorrow we have one by Vikram Halar from Human Career. He is going to speak on graph functions, also on graph functions, and so yeah, tomorrow's talk is from 11:30. So yeah, I hope we stay true to our schedule.